All right. Hello, everyone. I'm Sung, and I lead the managed Trino and Iceberg platform engineering team at Bloomberg.
I'm Antoine, and I'm an engineer in the managed Trino and Iceberg team at Bloomberg.
All right. Nice to meet you all. Thank you all for coming at this late hour today. All right, so last year at KubeCon, we shared how we built a secure governed Trino platform on Kubernetes by leveraging Open Policy Agent, a CNCF project. Over the past year, as adoption grew, the next set of challenges became very clear. Data governance was no longer our bottleneck. The real challenge had shifted to building a highly available data platform on top of our Trino clusters. That shift pushed us to evolve the platform from a single cluster governance-focused architecture to a multi-cluster deployment-based design, where high availability and data and disaster resilience are first-class concerns. So today, I'll set the context for that evolution, and Antoine will walk us through how we built and designed this next-generation Trino platform. Our managed Trino platform serves two primary personas. On one side, we have the Trino service owners, which is typically an engineering team that is defining and managing a Trino service, configuring the catalogs that they want to attach and the resource limits they want to launch the pods with. On the other side, we have the query user, who are the analysts, engineers, or applications that connect to a query endpoint and submit SQL queries. For both personas, the expectations are very clear. Trino service owners expect predictable lifecycle management, and query users expect a reliable query endpoint. In our previous architecture, meeting those expectations required those personas to coordinate those failures. The core challenge with Trino is that queries are stateful and tied to a specific coordinator. If that coordinator fails, the query doesn't transparently fail over, it is simply lost. So availability isn't something we can make perfect within a Trino system. But what we can do is to make failures predictable and make recovery and failover a responsibility of the platform instead of leaving it to the users. Let's briefly recap the single cluster architecture we shared last year. On a high level, Trino service owners express their intent to deploy Trino onto a cluster through an API. And within our platform, that intent is represented at two levels. The Trino service owners interact with a simplified abstraction called Trino service, which captures high-level intent, like the catalogs you want to attach, the resource configurations you want to launch the pods with, and the platform operator materializes that into the actual runtime, coordinator, workers, and networking configurations through a lower-level CRD called the Trino deployment. So within our model, the platform owns the deployment complexity, while users interact with a simplified API. Once the Trino deployment is running, a query user connects to a single query endpoint exposed by the cluster. Every query request is valued by an open server running inside the cluster, which retrieves policy bundles from a central policy store to authorize access. From a security perspective, this model works very well. But in this model, the platform did not yet factor in availability and resilience into the abstraction. Now we'll see what this means for the two personas. This means that when the cluster is unavailable, whether due to infrastructure issues or maintenance, the entire data platform was impacted. And that's a challenge that needs to be addressed when you start relying on Trino for production critical workloads. It's important to note that even in this phase of architecture, we did provide clusters in two availability zones. So Trino service owners, if they really wanted to, could deploy their Trino services in multiple zones if they wanted disaster resilience. That also meant that the query users would be able to continue submitting queries against the Trino pod, even if one of those zones were unavailable. Unfortunately, this meant that the responsibility of achieving high availability and disaster resilience were pushed to these personas. And this is because when a Trino service is reconciled, it exposed a zone-specific endpoint. You can see here that the endpoint returned is tied to a specific zone. So if a service owner deployed into two separate zones, they would retrieve two separate endpoints. And that meant that DR and HA existed if Trino service owners and query users implemented it in their own applications themselves. So instead, we'd want a Trino service status that looks a lot more like this, which returns a unified Trino endpoint regardless of which zone the actual underlying Trino runtimes are launched into. And that meant that our architecture had to evolve. We wanted to evolve from an architecture like this, where each persona operated against zone-specific APIs, right, into one that conceptually looked like this, where they interact with a single unified Trino API. And under the hood, multiple availability zones still exist, but failover, coordination, and high availability should be handled by the platform and not by these users themselves. And in this state, multi-cluster resilience becomes an implementation detail that is fully owned by the platform. So how did we actually build this? Well, as the title of our talk suggests, with Karmada and with Trino Gateway. Now that we understand the context behind the drivers that actually prompted our platform to evolve, Antoine will now walk through how we designed and built a platform that abstracts away availability zones and provides high availability and disaster resilience by default.
Thank you, Sung. Okay, so Sung walked you through the problems tied to a single cluster infrastructure. Now let me walk you through how to remediate to this. So we introduced the Trino API server. So the Trino API server is a stretched etcd backed API that served as the single source of truth for all the Trino resources. When a user creates a Trino service on our new federated endpoint, the service provider routes the request to one of our cluster. Since they now share the same stretched Z backend, both clusters are aware of the newly created resources. So we run multiple replicas of our Trino service controller for high availability, but only one of them actively reconcile at any time through Kubernetes leader election mechanism. So if a leader goes down, another replica picks up the leads and continues. So we achieve resilience without duplicate work. Our controller will then create what we call a Trino deployment CR. And we need to deploy it down to our stack into our Kubernetes cluster that physically runs the Trino pod. And so to do this, we rely on Karmada. Karmada is an open source Kubernetes management system that enables you to run your cloud native application across multiple Kubernetes cluster or cloud without change to your application. Karmada is also a CNCF incubation project with maintainer from a number of organizations, including Bloomberg. So last year at KubeCon China, we presented how we use Karmada across the organization, and our Trino platform is one of the key adopters of this technology. Okay, so on this slide, we can see that the Trino API submit the Trino deployment into Karmada. After defining what the propagation policies are for this Trino deployment CR, Karmada will submit the Trino deployment into the member cluster in order to build the Trino pods. Karmada continuously monitors the state of those Trino deployments, and if a Trino deployment in a member cluster becomes unhealthy, whether it's due to node failures, resource pressure, or any other issue, the controller detects and attempts to recreate the Trino pods. So Karmada is really the orchestration bridge between our declarative Trino API layer used by the user and the actual multi-cluster runtime that runs the Trino pods. So here's an example of a propagation policy. So it's a Karmada resource that tells the Karmada control plane how to distribute Kubernetes resources to member cluster. think of it as like routing roles for multi-cluster deployment. So in that spec, we are distributing Trino deployments, CRs, and our approach is to duplicate it across all member cluster. So all member cluster run Trino pods. So one important piece of our Karmada integration is how we aggregate the status of each cluster. For this, we use the resource interpreter customization. So we create a Lua script that teaches Karmada how to aggregate the status from the different Trino deployment across all member cluster. Okay, so to sum up the Trino service owner workflow. So the user creates a Trino service into the Trinos and submits it to the Trino API. Our controller creates a Trino deployment and submits it to Karmada. And then Karmada fans out the Trino deployment to the member clusters in order to create the Trino pod. Okay, so now we have Trino pods on each data center. And here comes the query users. And they want to query these clusters to access data. And so for this is where we introduced the Trino gateway. This is how users actually connect and run queries. So Trino gateway is a load balancer, proxy server, and configurable routing gateway for multiple Trino clusters. So it's backed up by a database that stores the key information that the gateway needs. It doesn't store data, it just stores configurations. The Trino gateway is also exposed through a filler endpoint similar to the submission endpoint. Our service provider routes the request to one of the data center Trino gateway pod. The Trino gateway pod then intelligently routes the request to one of the Trino pods. So under the hood, the Trino gateway handles dynamic backend management. So as Trino pods come and go, scale up, scale down, disaster happen, cluster get upgraded, the gateway automatically registers and deregisters them. All right, so that's a great feature. But so how do we integrate the Trino gateway into our stack, and how do we register Trino services to the Trino gateway? So when a Trino service is created and its pods come up healthy, the Trino service controller will create a Trino registration CR. This tells the gateway, hey, I'm a new backend, and here's my address. So this registration will be stored in the backend database that configures the gateway. So the Trino gateway pod can access it and start routing queries to it. All right, so now that's the point of this talk. It's like, let's walk through some component failures one by one and see how the system responds to them. So if there is a gateway failure in one of our data center, our service discovery detects that the gateway in data center 2 is unhealthy and start routing traffic only to data center 1. An important things to see here is that the surviving gateway in data center 1 can still dispatch queries to the Trino pod in data center 2. Only the gateway pod in data center 2 is down. So we only lost the gateway, but not the compute behind it. So now let's say that a Trino pod fails in one of our data center. Now the Trino gateway detects it and detects that the data center 1 pod is unresponsive and automatically routes query to the Trino pod in the data center 1. Once the cluster in data center 2 recovers, the Trino pod in data center 2 recovers, the gateway rediscover it and resume distributing queries across both data centers. Okay, so now let's say there is a Trino API server failure, or even worse, let's say the whole infrastructure is down, everything burned. It's not ideal. But what we're going to do is that we're going to bring back the nodes, we're going to bring back all the pods up, and because the underlying data lives in the external stretched CD cluster, which is independent of our API server, no state is lost. The API reconnects to etcd, our controller resync all the resources, and the system resumes operation as if nothing happened. So what are the key benefits for the user? For Trino service owner, they can deploy a single, simple manifest definition, and they can do it against a unified Trino API endpoint. The Trino services automatically recover from cluster failures, and the state is persisted in an external stretched service for rapid recovery. For query users, they also get a single endpoint via the Trino gateway. And this endpoint is highly available since queries are automatically routed to the healthy clusters. All right, so this is like our current release, but we still have like a lot of work ahead of us, and we're planning to extend our dual DC architecture to additional data center in order to increase fault tolerance and geographic distribution. We're also planning to work on optimizing our resource allocation. So Trino worker pod as statically defined today via an algorithm that we built. So we are working towards HPA-driven scaling that adjusts workers' replica based on query load, CPU utilization, GVM metrics, allowing cluster to scale up during peak demand and to reclaim resources during ideal period. And that's a discussion we just had, but we also want to start logging some queries via the event listeners and to capture and persist user query metadata. And lastly, we want to work on resource group enforcement to control query concurrency limits and queuing behavior. So the idea behind this is to prevent a single heavy query to monopolizing the cluster resources. Yeah, that's it for our talk. Happy to answer any question if you guys have. Sure, yeah.
Thank you for the presentation. Could you please tell how do you roll out updates, I mean like without downtimes? Do you update firstly one cluster, then another one? And second question I'd like to ask, why do you deploy Trino gateway in each cluster? Why not to have the one Trino gateway?
Yeah, that's such a good question. I'm so glad that we're thinking along the same lines with the community here. With this current release, we actually leave the responsibility of managing blue and green deployment entirely on them. So there's another layer of duplication they're going to have to own on top of this, this deployment because our current architecture doesn't factor in it. So if they really want to introduce a change, test it out against the same routing group first in the Trino gateway, that's on them. But we do have an item later this year where we want to look into how we can leverage Karmada propagation policy or other tools that are within the landscape to see if we can do exactly that, which is to deploy to one side first, define some rules to make sure that there is going to be one side that is still active and healthy, right, before we continue to roll out the change to the other zones as well. Yep.
Hey, hello. Can you hear me? I wanted to test how we do automated tests of disaster recovery. Do you use any frameworks for this, like Terra test, or how you validate that entire disaster recovery works?
Could you repeat the question? Sorry, there's a lot of echo. Yeah.
Sorry. How you ensure that disaster recovery in the end works? Do you have any automated tests or automated frameworks for this?
Yeah. So we do have kind of scheduled end-to-end tests and release-based end-to-end tests. By your question, did you mean like when we bring back up a cluster, we're verifying that a zone is still active in the way we need? So Trino Gateway actually already has a baked-in application logic to detect when a specific backend is healthy or not. So within Trino Gateway, it actually has the application logic to understand if a backend is healthy enough for the queries to be routed back to it again. That's the logic we're relying on for that. Yeah.
Hello, thanks for the talk. How you protect against the Karmada cluster being out? For example, if the cluster, Karmada, that hosts Karmada, if it's going down, the control plane, I mean, Karmada cluster, if it's going down, what would you do?
So I guess the question is like, what if Karmada goes down, right?
Yeah.
So Karmada at Bloomberg is a managed service. So we do not, as a Trino team, manage directly Karmada. We're using them as a service. And they provide SLOs on their side that we're using their prod.
Do you know how they do it?
I'm sorry?
Do you know how they do it?
How they do it? That's going to be a great question for the Karmada folks. they're in the room, by the way, so feel free to ask them like at the end of this talk.
From your diagram, I understood that as a Trino service owner, my interaction is with the top cluster, with the stretched CD. But the deployment is actually done by Karmada in multiple clusters. How do you transmit, if something goes wrong with the deployment of the Trino service in one of the clusters, how do you reflect that information all the way up to my interface, which is the top cluster?
So the way the flow works is that once it's down there, and there are statuses, our Lua script is taking care of the aggregation layer. So then Karmada reflects this in the status of the Trino deployment. And then our controller has a watch on Karmada API server to every time there's an event that is kicked off, we are taking the status of Trino deployment and updating the status of the Trino service so the user can get that status. That's correct. So I can go back to the design here, and I guess where the Trino service controller is here. So we have the Trino service controller there, and this controller, when we set up the manager, we make it like look for events that are happening on the Karmada API server. So if there is a change on the Trino deployment, they will emit an event against the Karmada control plane, and our controller will be watching that API server and then reconcile.
I want to ask what Trino Gateway has more than Gateway API of Kubernetes.
Yeah, great question. So Trino failover is a tricky thing. So from the client side, when you initially submit a query, you don't have a query ID. And the coordinator that receives it actually returns you the query ID you're supposed to use for the next page and so forth. So there's a little bit of application logic, right, for routing Trino queries to begin with. And then on the other side, for you to kind of manage the draining process of Trino. There is also a little bit of application logic that is baked into Trino Gateway that allows you to tag certain backends as being inactive, which signals the queries that are currently in process, right, to complete, still be routed to that inactive backend. while the newer queries are prevented from being routed to that one. So that if you have certain query limit to how long your queries can be, you have a window of time that, if you drain a cluster in this state, managed through the Trino gateway, you're guaranteed to not have to interrupt any of the queries and drain it successfully. So that was exactly the reason why we decided to go with Trino Gateway, because it is an open source project within the Trino community that has developed this application logic. And of course, if you deem that you want to go with an Envoy gateway, for instance, and implement that logic yourself, that is absolutely doable as well.
I have two questions. Have you considered using something more than just deployments, something like Argo CD, or even something more complex than just a deployment, Kubernetes deployment? And second question is, how easy is it to expand your compute to 3 clusters instead of 2 of them, just in case 2 of them is not enough anymore?
So I guess the first question is like, why not integrating Argo into our workflow? So there is not a huge need for us to do that, because this is a pretty simple workflow. This is just like a controller submitting a CRD into Karmada, and then Karmada spanning it out onto Kubernetes clusters. So we didn't see the need of integrating with Argo. And then the second question, was around. Yes, that's correct. So it would be pretty easy. So on our side at Bloomberg, we rely on something called KaaS, Kubernetes as a service. So the idea is that we can just take a spec definition of a Kubernetes cluster and just create it by requesting some machines that would deploy our whole stack. So we also have a deployment tool that is called Babka, and that helps us to basically just add the configuration of the cluster, and then the whole stack will be deployed on that cluster. Then the last step would just be to make sure that Karmada knows about this cluster. So when we integrate with Managed Karmada, we just need to let them know, it's obviously via their API, to be like, hey, I want to register that cluster because now I extended my geographic distribution. So please register that new cluster in there. And then it will know that I need to deploy a Trino deployment into that new zone that will register against the gateway, and then the two workflow for Trino service owner and for query user would be exactly the same.
I have another question about this stretched etcd deployment. Can you expand how it is implemented? From what I see, it is basically a single point of failure for an entire deployment, because you just shifted logic in.
Sorry, I didn't get it.
No, can you expand about stretched etcd implementation, how it works?
Yeah, so same thing at Bloomberg. There's another managed services, which is Stretch etcd as a server, where basically you request an allocation, and they provide etcd. And then what we did is that we have a Helm chart that is installing an API server. So what you see in there, the Trino API server, is actually just a pod. And it's a pod that is configurable, that act like an API server, where you can enter the certificates to connect to it, and where you can reference a Stretch etcd endpoint. So the idea is that this pod will then act like an API server, and swap the local etcd just to point to etcd server.
Just to answer that a little bit more, there's actually kind of industry parallels so that we kind of highlight what you can actually use outside of a managed ecosystem. Kind API server that can run on Postgres, right, where the actual data is replicated across multiple zones is a good parallel for you to be able to adopt if you're thinking about implementing something similar.
But this etcd pod is deployed in both clusters, so you have like two etcds.
Yeah, so we basically set those two pods to share the same kubeconfig, so to share the same certificate. So if a request is coming to our service provider, it will go to one of the pod, and since they share the same like stretch HTTP backend, both pods are going to be aware about this newly created resources. So they share the same kubeconfig basically.
Yeah, I think just to kind of tie the note on that point, the key idea there is that different clusters just store and share the custom resource persistence into a single source of truth that is still distributed and highly available. Yeah, Postgres and Kind offer a similar approach, as long as the Postgres instance itself is actually replicated. Yep. All right, I think that was all of the questions. Thank you all so much for coming to the talk so late in the day. Thank you.